think we can get started for the session 1. And the first speaker is Duncan Lorimer from West Virginia University. Duncan, can you hear me?
Yes, I can hear you guys.
Could you please share your screen?
Yeah, I'm just trying to do that. Oh, I see. I've got to just take one more step here. A sec. Okay. I'm sorry. It's saying allow WebEx to share content, but quite sure what to do. Sorry.
Are there anywhere that we can share from us?
Yeah, maybe if somebody could just project from there. I've uploaded the slides. I'm sorry, I feel like an old person. I am an old person.
No, Duncan, you look great.
Well,
Formal.
Yeah. Right, I can see the screen in the distance.
Okay, hold on now.
Yeah.
Okay, so please try let us know if you want to change to the next slide. Okay.
Okay, great. This is like the old days when they had a slide projector and you would have asked the person to use the slide.
Yeah, no worries.
Thank you very much.
Yeah, no problem.
So yeah, good morning, everybody. Thank you so much for inviting me to this meeting. I'm sorry I can't be there in person. It's wonderful to be a part of this, and it's my pleasure to kick off this wonderful program of talks that you all have. And I wanted to try to set the scene in the next 20 minutes or so, talking about the past, present, and a little bit about the future of the field, which, as we've been hearing in the introductory remarks, is still relatively nascent, about 15 plus years ago now, since this all started. So I'm going to be talking about the early days, going back to pulsar astronomy before fast radio bursts were discovered. Talk a little bit about the discovery of fast radio bursts, and then get into some of the applications, which we're going to hear a lot more throughout the week, and in particular look at some of the identifications of fast radio bursts with host galaxies, and then look ahead to some of the future challenges. So if we can go on to the next slide, please. So yes, this just summarizes the current state of play regarding the facts, the essential facts that you need to know if you're just getting into FRBs. What we're talking about here are sources of radio emission. So what you're looking at in the background there is the radio sky from the horizon close to where I am here in West Virginia. This is the Green Bank Observatory site. And then in the sky in the background is the radio sky at 5 centimeter wavelength. And what you're looking at there are not stars, but mostly galaxies. And then those extended sources are radio nebulae, such as supernova remnants. So it's a very different picture to what we see optically. And the FRBs, so what you're looking at there are the steady sources that are there from night to night. The FRBs are relatively bright, but transient sources that last only a few milliseconds typically, but are observable across the radio band from down to the FM, and, a few hundred megahertz or so, up to several gigahertz now. And they're most readily observed at around a frequency of around a gigahertz, but below and above there are instruments that are doing wonderful things, as we'll hear. Based on the amount of sky that can be covered by radio telescopes, accounting for the fact that they don't see the whole sky all the time, we're converging on a rate now where thousands of FRBs are going off pretty much uniformly across the sky. Once you account for exposure effects, there's no preferred direction on the sky. They're highly dispersed pulses, and we'll look at the dispersion in a few moments. And to date, in the literature out in the public domain, there are 639, I believe, currently published FRBs out there, and a few thousand coming soon from further experiments, in particular CHIME, which we'll be hearing a lot about. About 50 of the known FRBs so far are known to repeat, and about 24 of the FRBs have very robust associations with host galaxies whose redshifts we can measure. If we can go to the next slide, please. So, going back to 1968 now, I want to take you really back in time, over 50 years, to the discovery of pulsars. Just very briefly, what you're looking in the background there is the Crab Nebula, the remnant from 1054 AD. And superposed on there are some radio pulses. This is a nice image made by our colleagues at Astron, showing giant pulses from the Crab pulsar that's in the heart of this nebula. So this pulsar is about 1,000 years old. It was produced in that supernova explosion, of course, and shortly after its discovery, and in fact through its discovery, it was found through its emission of bright individual pulses. So this was a really key aspect of pulsars that was known very early on, that some of the sources will emit pulses that are many times brighter than the mean, sometimes thousands of times brighter than the mean. And so astronomers quickly caught onto the fact that as they were discovering pulsars, they could detect potentially these giant pulses from much further away, well beyond the Milky Way. If we go to the next slide, people were thinking about the implications for this in the early 70s, and Ginsburg, in this prescient paper here from 1973, was talking about what we could do if you could see these radio sources that were showing similar dispersion to what we see in the pulsar field, and in a very similar way to how we measure the interstellar medium in the Milky Way from pulsar observations. We can measure through measurements of dispersion the intergalactic material, and we'll hear a lot about that this week. So that possibility was first explored by Ginsburg as long ago as 1973. So if we move one more forward to the next slide. This is a high school experiment. Back in 1979, a young high schooler named Sturl Finney, now a Caltech professor, was working with then a college professor at UMass Amherst, Joe Taylor, on a project to search radio data that Joe had discovered the binary pulsar in, which subsequently, along with Russell Hulse, garnered the Nobel Prize. But from that survey, they were also analyzing for individual pulses, and carried out one of the first searches for individual pulses that had high sensitivity. And they were motivated by a number of astrophysical sources, such as evaporating black holes that are shown schematically here that might emit an electromagnetic pulse, and other things such as distant supernovae. No pulses were found in that experiment, but it kind of set the scene for further experiments over the years. And if we go to the next slide, fast forward to about 20 years ago, a lot of pulsars had been discovered by then. Pulsars had become their own field, and many pulsar people are at this meeting, of course. But people were going back to this idea of looking through the much higher sensitivity data that had come about by then for individual pulses. And this picture of Jim Cordes and Maura McLaughlin and Shami Chatterjee were, and that lab, in fact, it looks very much the same as it today, with a picture of Babe Ruth in the background, and Jim and Maura and Shami look pretty much the same today. But they were, back in those days, they were looking at the possibility, again, of finding crab-like pulses from distant, very distant sources. So they published this paper in 2003, Jim and Maura, on searches for fast radio transients. And that kind of energized the community. If we go on to the next slide, shortly after that paper was discovered, rotating radio transients, or RRATS, were discovered by Maura and collaborators in 2006. There's a paper that describes the discovery in archival data of individual pulses in the Milky Way. And you can see the dispersion effect here, where the highest frequency, frequency versus time, the highest frequency parts of the pulse arrive first. A rule of thumb that any pulsar astronomer will be able to tell you is that the dispersion measure, which is defined here as the integrated column density of electrons along the line of sight, if you divide that dispersion measure by 30 in the units of dispersion measure of parsecs per cubic centimeters, if you divide that dispersion measure by 30, you get a rough estimate to the distance in kiloparsecs. There's an analogous expression for FRBs that I'll talk about later on. But this was really proof that the existing data sets had new sources to be discovered. If we go on to the next slide, shortly after Maura and I moved to West Virginia years ago, we started looking through more data and found with an undergraduate student, David Narkovic, there, the first of the fast radio bursts. And you can again see the radio frequency time sweep. And we had just a sample of one object. Fortunately, I'd been used to working with small samples of objects, but nevertheless, it was a tough sell to make, tough case to make, that we had found the prototype of a new source population, and there's a lot of nuance to the story. But if we just go to the next slide, 20 years or 15 years later, we now have what's known as the Lorimer burst, was mentioned in the introduction, has now come into semi-popular culture as a German instrumental post-rock band. Now goes by this name, and you can catch them in those tour dates last year. So it's been a very interesting story that I'll fill in the gaps between then and now. If we go on to the next slide. It's very interesting that we really just found that first source, but and using more advanced and just better single pulse detection techniques. This paper came out a couple of years ago showing another source in that original data set that would have really helped make the case a lot stronger initially, and perhaps even advance the field more rapidly. If we go on to the next slide, this shows what's currently, I think, the earliest reported sightings of an FRB. And these go back from data taken in the 1990s, also with the Parkes telescope at 70 centimeter wavelength. Fernie Crawford and collaborators shown here reanalyzed those data. They were actually part of my and other PhD theses in the 90s. We were looking for pulsars, but they had these individual bright pulses present in them that have now been revealed to us. So FRBs really have been around for a while. It's just taken us, a little bit of good fortune and then further follow-up to exploit this hidden population. So if you move on to the next slide, about 10 years ago, a very important paper came out from Thornton et al. That put into context the initial discoveries. In that paper they announced 4 new fast radio bursts and really coined the name of the sources at that time. They really, at that point, you had a population of their 4 sources plus our original one and one other. They're shown there as a distinct population in dispersion measure versus galactic latitude, very distinct from the radio pulsars in our Milky Way, which is shown in red there. And so really for the first time we have this cosmological population where that excess dispersion measure that looks very anomalous in this plot can be attributed to the intergalactic gas that Ginsburg was talking about 30 years earlier. And as a rule of thumb, I don't have it on the slide here, but as you go through this week, if you divide the dispersion measure of the FRB by 1,000, you get a very rough estimate, I stress the word estimate, of its redshift. We'll look at some measurements of the redshift in a moment. But this was a really, needless to say, this was a really landmark paper that kind of accelerated the field 10 years ago now. So if we go on to the next slide, what happened shortly after that was that FRBs started to be found with other telescopes, and one in particular that was found with the Arecibo telescope from data taken in 2012 was shown in 2016 that the source actually repeats. Up until that point, we had about 5 or 6 to a dozen FRBs that were known just from single detections. Despite follow-up that was very erratic, there wasn't really a clear indication that they repeated until this first detection in this source here. That was very instrumental in again moving the field forward, because it tended to rule out cataclysmic sources for these types of these repeating FRBs as they're now known. And it points to perhaps a recurrent phenomenon from a giant pulsing source. But if we go on to the next slide, another really important application of this repeating phenomenon was that you could stare at it with much higher radio angular resolution using the VLA here, and Shami Chatterjee and others had this magnificent detection of the FRB with the VLA a year after that earlier paper in 2017, where they were able to pinpoint the position of the source such that they could locate it to that host galaxy that's shown in the top right there, and measuring the redshift of that host galaxy, you get a redshift of 0.19, and that was the first really robust indication that these FRBs were truly extragalactic and indeed cosmological sources. So if we go on to the next slide, we're starting to move into the last few years of up until the present day. Around that time, the ASCAP telescope, the Australian Square Kilometre Array Pathfinder, was coming online in Australia and had an amazing potential for FRBs among its other science goals. And in 2018, it basically doubled the population of FRBs known at the time. And the sample is shown down there in the graphic. It also started to fill in the phase space, if you will, of what's shown here as fluence versus excess dispersion measure, the dispersion measure beyond the Milky Way, and kind of gave you an indication that there is not a standard candle relationship of FRBs, but a range of luminosities of the sources. But it started to put some energy, it started to really get a good statistical sample from which to do population studies. We're going to be hearing about those throughout the week. I think Clancy is giving a nice review of the populations of FRBs. So if we go on to the next slide, one of the amazing results from ASCAP that was started by one of its founders, J.P. Macquardt, is known as the Macquardt relationship. It's basically a plot of, for those FRBs with robust determinations of redshift, plot of dispersion measure, excess dispersion measure versus redshift, and you see the clear correspondence between those two quantities that maps out those baryons in the intergalactic medium. And that was such a fundamental plot that it was the first time this had been really been measured, and it's in honor of JP's memory, who sadly passed away in 2020, the Macquardt relation is now what that's known as, and that is being studied in greater detail. The variance in that relationship is a very interesting property to study now as more FRBs are found. If we go on to the next slide, this is a nice schematic of the different types of DM distributions that you might expect from a cosmological population of FRBs. If the halos of galaxies are extended, as shown on the right, there's more bell curve-like populations.
Left.
Thank you. Yep. And if they are less extended, you get more of a tail, as shown there on the left. And so this graphic just gives you a flavor of how you can use the FRBs to begin to study structure on cosmic scales. So if we move on to the next slide. CHIME, you'll be hearing about a lot this week, has revolutionized the field in terms of the number of sources, and you can see a graph of number of FRBs versus time, and it spikes up there as the instrument was switched on and produced its first catalog, basically discovering on average about 3 sources a day. Many repeating sources, but also many one-off sources. If we go on to the next slide, this is a schematic that shows 4 different types based on the burst morphology. So you're looking at frequency versus time, and you see on the left there what is typically the one-off sources, and on the right you see what's more characteristic of repeating sources with these narrow band signals, and in particular on the far right there, this downward drifting of the individual subpulses. So that's provided a lot of clues about the morphology of the population that are now being studied. If we move on to the next slide, as I mentioned, we have 24 FRBs with redshifts. This is one of the most nearby sources that was published in 2020 and shows the FRB here in a spiral arm of a nearby galaxy. The FRBs turn out to be ubiquitous in many different galaxy types, but now we're getting a sample such that you're able to study the different environments in some detail, and we'll be hearing more about that this week. If we go on to the next slide, this particular source is also periodic in the sense that the pulses themselves don't have a strict periodicity, but there is a periodicity in the activity windows. In this case, I believe it's 16 days, and so it suggests some sort of driving periodicity, perhaps due to binary motion or a processing source there. And it's one of just a handful of FRBs that show this phenomenon. But it's really hard to reveal this type of periodicity. It takes a lot of follow-up observations. If we go on to the next slide, 2020 was also a banner year for FRBs. It was a bad year for the Earth, but there were a lot of really interesting FRB discoveries. This one here in particular is the Galactic FRB source that looks like an FRB, but is basically is coming from a magnetar that was conclusively identified as a magnetar in the Milky Way. So that was a fantastic result by both STARE-2 and CHIME in 2020. Just in the dying moments of the talk, if we go on to the next slide, we're seeing FRBs in many different environments, including globular clusters now. Here's one from a beautiful publication showing a source in a globular cluster in M81. So again, you have this just a diversity of environments in which these sources are being produced. And if we go on to the next slide, we're starting to see quasi-periodicities within bursts. Here's some very nice examples that were published by the CHIME FRB collaboration a couple of years ago now that show subpulses, let me call them that, that have a quasi-periodicity within a single burst window. So you can see that the extent of the resolution now that is really quite exquisite in some cases. Just a result that's currently unpublished, but I just wanted to show you in this context. If we go on to the next slide, here in West Virginia, we have an experiment on the GBT. This is what we call GREENBURST, and it's basically piggybacking on the telescope and collecting data 24 hours a day, and where we have a very small field of view but quite good sensitivity. And we picked up an FRB recently that has this sort of quasi-periodicity to it as well, as it's shown here. So there's a lot of interest in these sources, and we're revealing more and more information as we get to higher time and frequency resolution. On the next slide, this shows the phase space of these transients. And you can see at the shortest time scales now, we're able to resolve FRBs at the microsecond level and even below that. And so we're seeing extremely fine time resolution that's providing these different islands here in this phase space. And so, we've discovered a lot in the last 15, 20 years, but we're still starting to. It's still important to remember that we're really trying to fill in the information here, and there's a lot of opportunity ahead as the telescope capabilities grow. In my last couple of slides, I've just got some open questions that I won't dwell upon. But if we go to the next slide, I just wanted to throw out some of the big questions. Do all FRBs repeat? How many populations are there among the FRBs? I think that there are a lot of different environments that I've highlighted here in this brief overview. What are these studies of host galaxies telling us? We're going to be hearing the latest about that this week. Periodicities. There's been reports of FRB counterpart to a gravitational wave source, which is very exciting. That came out very recently. Like pulsars, will we ever understand the FRB emission mechanism? There may be many different types of FRBs, different types of sources, but just also like pulsars, we'll be able to use them as probes to study different physical phenomena. So with that, I'll just go to my last slide and just remind you all, kind of preaching to the choir really here, but the future is very bright. There are a lot of wonderful observatories that are in existence or coming online, just a few of them shown here. The next decade or so, we're already at the level of thousands of sources and dozens of identifications and redshifts. I think it's really exciting to start to look for counterparts in real time outside of the radio regime, and to think about different timescales for these transient phenomena. If this overview has given you any type of a sense, it's that we really are on the precipice of our understanding. And I think 10 years from now, when we come back here and review, we will have discovered an even wider swath of this phenomenon. But I think we're at a fascinating time, so that's probably a good point for me to stop. Thank you very much.
Thank you. Excellent review for the FRB. Let's take just one question and move on. So, any question? Yes.
Thank you, Duncan, for the wonderful chronological understanding of FRBs. So I'm very curious to know what should be the next step for the FRB community to look at for the next discovery or something more of astrophysical importance? I mean, I'm just curious to know your opinion. In which direction should FRB community move on?
Well, that's a great question. I think, you know, it's certainly a matter of opinion, and I think it's casting a wide net. We have, you know, some amazing abundance of talent in the community right now. People are trying many different approaches. I think it's a field where small and large telescopes can contribute in new and interesting ways. You know, what really interests me quite a lot, I don't really have much time of my own to get into it, but I hope to learn a bit more this week, are really the prospects for simultaneous optical and radio observations. I think that's really interesting. And really then any other simultaneous observations outside of the radio band, looking for these, what I would call prompt counterparts of transient sources outside of the radio band. I think that'll be very interesting.
Okay, great, thank you, Dunk. Yeah, so let's thank Dunk again, and let's move on to the next paper. Dilly, are you on?